Dear colleagues, my name is Alejandro Suárez Mascareño. I am a postdoc at the Instituto de Astrofísica de Canarias. My work focuses mainly on exoplanet detection and the study of stellar activity. Currently, I am dedicating most of my efforts to the exploitation of the guaranteed time observations of the Espresso spectrograph. Today, we will be revisiting Proxima with Espresso. Proxima, the closest star to the Sun, is a small M-dwarf located just 1.3 parsecs away. It is the smallest of a triple system, with Alpha Centauri A and B. Its mass is just 12% of the solar mass, and its effective temperature around half of the Sun. The small mass makes it quite faint despite of its closeness. Among the main differences between Proxima and the Sun, we have its rotation period of around 83 days, more than 3 times slower than the solar rotation. The discovery of an Earth-mass planet orbiting the habitable zone of Proxima was one of the most important events in exoplanet sciences in recent years. A team led by Guillem Anglada-Escudé found an 11-day signal using years of radial velocities acquired with HARPS and UVES. The planet was detected using the radial velocity technique. When a planet orbits a star, both move around the barycenter of the system. If we take a series of spectra, we can then detect this movement by measuring the Doppler shift of the spectral lines. When we see that this Doppler shift is periodic, we have the indication of the presence of a planet. This was the technique used by Michel Mayor and Didier Queloz in 1995 for the discovery of 51 Peg-b, which granted them the Nobel Prize. In the case of Proxima, the discovery pushed the capabilities of the HARPS and UVES spectrographs to their limits. The amplitude was so small that it was comparable or smaller than the error bars of most measurements. The signal would correspond to a planet of 1.3 Earth masses orbiting with an equilibrium temperature of 230 Kelvin. It meant there could be a potentially habitable planet in our nearest neighbor. Confirming it became a very important task. Enter Espresso, the new generation spectrograph capable of measuring radial velocities with a precision never seen before. Espresso is installed at the ISO-BLT array of the Paranal Observatory. This array consists in 4 8-meter telescopes. The instrument can take the light of any of the telescopes at any given time, or even from the 4 at the same time. Espresso is isolated from thermal pressure and mechanical changes to ensure the best possible stability. This stability is key to ensure the never-before-seen precision that Espresso aims for. Back in 2003, the HARPS spectrograph improved the radial velocity precision on its time by 1 order of magnitude, opening the gates to the detection of Neptune-sized planets, super-Earths, and in very specific scenarios, Earth-mass planets. Espresso is once again providing an order of magnitude jump in precision, this time opening the gate to the detection of Earth-mass planets in the habitable zone of Sun-like stars. Proxima became one of the first targets for the Espresso guaranteed time observations. We obtained 60 measurements during 2019, with the goal of confirming the existence of Proxima b and to explore the presence of additional companions in orbits close to the habitable zone. Here you can see our data, combined with the archival HARPS and UVES data. On the right, there is a zoom to our 2019 campaign. In the top panel, you can see the radial velocities, and in the lower panel the full width half maximum of the cross-correlation function, a metric we use to follow the changes in stellar activity of Proxima. If you look at the right panel, a periodic variation is already evident by eye, the 83 days rotation. The first thing we did was trying to detect Proxima b with our data and only our data. We modeled the activity with Gaussian processes using a combined fit between the full width half maximum and the radial velocity. This combined fit helps leading the Gaussian processes to model the signals related to stellar activity, even if those signals are not the most significant signals in the data. With this approach, we quickly found the rotation, And if we study the residuals of the data, there is a significant peak at 11.2 days, exactly the place where Proxima was expected to appear. When modeling activity and a Keplerian together, we find one of the most beautiful and clean radial velocity curves I've seen in my life. If we add the archival data, the result remains consistent. You can see here the difference in quality of the radial velocities produced by Espresso and the radial velocities produced by HARPS. In both cases, the white noise component used to model and accounted error sources has been quadratically added to the error bars. The phase-folded curve is by no means less impressive. Combining all the data makes the difference even more staggering. Thanks to the collecting power of the VLT, we could split the spectra into 3 different bands and obtain colored radial velocities with a precision still better than half a meter per second. When we compare the amplitude of the 2 detected signals in the different bands, we see that they don't behave exactly the same. The signal related to the rotation has an amplitude that decreases once we move into red wavelengths, while the signal attributed to the planet has a very stable amplitude across all the spectral range. This is caused because once you have a signal caused by spots, the amplitude of that signal depends on the filling factor but also on the contrast between the spots and the photosphere. Once you move into red wavelengths, the contrast decreases, meaning that for the same filling factor, the amplitude you are measuring is smaller. This is further evidence that the 11-day signal is not caused by stellar activity, but rather by a planet. We can also create chromatic velocities just by subtracting the blue component minus the red component, or any other combination. If we do that and we analyze the result, we see that there is one dominant periodic signal exactly at the rotation period. This could be a very powerful diagnosis to disentangle between planetary and stellar-induced signals, at least in the case of spot-induced signals. With our measurements, we are now able to independently confirm the presence of Proxima b with a minimum mass of 1.2 Earth masses, which for all we know probably looks something like this. But there's more. As I told you before, we were looking for additional companions. We found evidence for an additional signal with a period of 5 days and an amplitude smaller than half a meter per second. This signal, if caused by a planet, would correspond to a planet of around 1/3 of the mass of the Earth. We did not find evidence to link it to stellar activity, but sadly our data was not enough to confirm the finding. So now what? We are preparing an effort to observe Proxima to confirm the 5 days planet, and to better characterize the orbit of Proxima c, announced by Mario Damaso early this year. Before diving into the questions, I would like to emphasize that this has been the result of the effort of many people. The Espresso project started more than 10 years ago, when I was not even a PhD student, and I've been fortunate enough to be able to participate in the beginning of its scientific operations. Without all the people listed here, this would have been most likely not possible. And with that said, let's jump right into the questions. Thank you very much for your attention.